Welcome to my presentation about how to discover relevant process details from image data through association rule mining. My name is Myriel FICHTNER from the University of Bayreuth in Germany, and today I present the results of our novel approach. Industrial as well as small and medium-sized enterprises use process models to visualize workflows. They may include different types of actors, for example robotic as well as human workers. However, due to the demographic change and a trend towards small batch production of goods with high variability, the process models have to be adapted often, and the control flow needs to include many specific alternatives. This can lead to large and hardly traceable process models, which can only be created with high effort and thereby complicating the instructions for humans. To overcome this issue, abstraction mechanisms are used. However, these abstractions come with a loss of information, while important details can get lost. In a worst case, such details are so-called relevant process details that have an impact on the process success if not considered during task execution. This process knowledge must be revealed and incorporated into a model to ensure the accurate execution of a task. Thereby, relevant process details can be used as task specifications for a given process model to further refine existing task instructions. For example, as shown here in a placement task, a relevant process detail may describe a certain region of the goal location. Objects have to be placed in the upper half of the plate to achieve process success. Identifying such a process detail that is missing in a process model but that would improve process success if considered while modeling is related to the topic process model improvement. We classify existing research in this context in intrinsic and extrinsic process improvement approaches. Intrinsic approaches are techniques which use known information to improve processes and underlying models. They mainly include optimization approaches on the model itself, like for example reducing the number of modeling elements in a model. Please note that the list of existing papers shown here is not limited. However, most business analysis tools are restricted to a single data source. In contrast, there are only a few extrinsic approaches which take further data sources for process model improvement into account. They have the advantage that they can also analyze non-modeled but relevant information of a process. We also classify approaches such as BPM and EASY as extrinsic, which supplement existing process modeling languages by adding representation options for data from further sources like images or videos. However, there was no approach which covered the identification and extraction of relevant process details from execution data. Therefore, we developed a concept in previous work which I want to introduce briefly. Our developed concept describes an iterative approach where relevant process details are identified by analyzing tasks in a process model successively. The input of our approach is an existing process model PM, which contains a set of tasks which have to be executed to achieve a certain business goal, for example, manufacturing a certain product. In the preparation step, a subset of tasks is extracted from the set T. This subset comprises tasks that describes process steps requiring manual execution by workers. We assume that such task instructions may lack essential information. In turn, from this set, a single task is selected for further analysis in the definition step. Further, a data source in the process environment is chosen, which will be used to record execution data of the considered task. For example, if a camera system is selected, image data is collected during process model execution. Then, the process model is executed as prescribed, but data during the execution of the selected task is recorded. At the end of one execution run, this collected data is labeled regarding process success. This procedure is repeated until enough labeled data is collected. Then the set of labeled images is analyzed by using an appropriate technique. In previous work, we trained a convolutional neural network and used explainable AI to determine the reasons for the assignment to a positive class label. The result is a rule or a similar construct which contains relevant process details that have to be considered during the execution of a respective task to achieve improved process success. This information is then attached to the process model as task annotation, for example as a simple text attachment, leading to an optimized process model. The procedure can then be repeated for other tasks as well. Although the results of our previous implementation with convolutional neural networks was quite promising, it comes along with two main drawbacks. First, it mainly focused on unstructured data with the example of image data. There, additional steps were necessary to extract a rule containing the relevant process details from the analysis results. This objective can be more effectively addressed through structured approaches. Second, the previous approach is accompanied by certain requirements, one of which is the need for a substantial amount of data to train the neural network. Nevertheless, this requirement remains unfulfilled in small enterprises, while an alternative approach is needed, tailored to such scenarios. For this reason, we suggest an approach with association remining for the analysis step of the overall concept. The goal of association remining is to identify interesting associations between items or item sets in a database. While we will use this ability to identify relevant process details, we will come back to this in a bit. Association remining was initially employed to assess customer behavior through market basket analysis, as shown here in the example. The result is always an association rule in the sense of a mathematical implication. This implication has an antecedent, the left side of the implication, and a consequent, the right side of the implication. It can be read from left to right in the sense of a if-then rule. The analyzed rule in the provided example on the left can be interpreted as follows. Customers purchasing diapers are likely to also buy beer. Supermarkets can utilize this information to strategically relocate their products. The challenge of association rule mining is to find only interesting rules. Therefore, several evaluation indicators have emerged which can be used to assess the quality or strength of a rule, such as support, confidence, Kulczynski, and so on. In the following, we will show how we use association rule mining on structured image data to extract relevant process details. Our concept consists of 3 steps. First, the input data needs to undergo preprocessing. In cases like ours, where unstructured data such as images is examined, it must be transformed into a structured format. For images, this transformation can be achieved through computer vision approaches, which identify objects and their features within the image. Second, the data needs to be converted into a one-hot encoded format to be compatible with association rule mining algorithms. This second step is also necessary for structured data if it is not already in that appropriate format. Then, association rule mining algorithms are applied. For the evaluation, we selected some algorithms where only algorithms that can cope with classification problems are considered. Further, due to the presence of quantitative attributes coming from object features, they must cope with large databases containing numerical data. Please read the paper for further details regarding the algorithms. We generated only rules which have the positive label in its consequent. Since we consider only a 2-class problem in our experiments, the label 0 indicates negative process result and 1 indicates positive process result. The rule generation step typically generates more than one rule. This is inadequate, since we aim to generate concrete guidelines later being attached to process steps. Workers will have difficulties to resolve situations when confronted with situations involving 2 or more concurrent rules. Thus, our approach selects the best rule that constitutes the output. The quality of a rule is determined by applying different evaluation indicators. We then select the rule that has the highest value regarding one or multiple evaluation indicators and call this rule relevant rule. To evaluate our approach, we designed 2 use cases which correspond to the experiments of our previous implementation. The use cases show pick-and-place scenarios from manufacturing environments. We assume that images after the execution of a pick-and-place task are collected and labeled at the end of the process. Furthermore, the task description was too narrow, containing only the information that objects have to be placed, but does not specify which objects have to be placed and where they have to position exactly. In a first use case, workers have to place one of 2 available parts on a tray. In our experiments, the parts differ only in their color. Scenes with blue parts result in positive outcomes, while those with green parts are labeled negatively. Parts can be placed anywhere, but must be fully visible. Therefore, this use case comprises one relevant feature, the color. Our objective is to investigate whether a relevant rule containing the blue color information can be found to extend the task description. We implemented 4 different variants of this use case to evaluate the impact of certain factors like noise, reduced sample size, and unequal distributions. In a second use case, the task is again to place parts on a tray. Unlike in the first use case, this use case specifies that 4 parts have to be placed, but again not their exact placement on the tray. The relevant process detail refers to constellations that at least one circular part has to be placed in the upper 7th of the tray. Therefore, 2 features, the shape and position, are crucial for process success. In this specific use case, the anticipated rules will exclusively encompass the object's positions. This is due to the fact that the assignment to the object and consequently its shape is determined by the position values, which inherently correspond to a specific object. We implemented 2 different variants, once with a huge and once with a strong reduced sample size. We applied our conceptual approach and the selected association rule algorithms as stated before and evaluated the 2 use cases. For the algorithms, we considered different hyperparameter sets using a grid search. To compare the results and to reveal the applicability of the different association rule mining algorithms, we focus on 4 criteria. First, if the relevant rule was found at all or not. Second, what percentage of hyperparameter sets do not discover the relevant rule. Third, how many rules were found with a positive label in its consequent to determine the number of competing rules. And fourth, if one of the considered evaluation indicators helped to select a rule. If exactly one rule was found, this criterion is automatically fulfilled. Further, we investigated if the inclusion of an additional pruning step within the rule generation procedure improves the results. All values are shown in the tables, while we conclude the results briefly. For use case 1, the FP growth and the quant algorithm are robust against hyperparameter changes in the non-pruned case, but produce competing rules. The hyperclick algorithm finds the relevant rule in all cases, but is sensitive regarding hyperparameters. GAR plus with pruning leads to insufficient results. The evaluation indicators do not support the selection of a rule. And finally, all algorithms excel with small data, what can be seen in variant 1.3. For use case 2, the FP growth is robust against parameter changes in all cases, but generates too much rules without pruning. Quant does not generate rules in adequate time. This means below 24 hours, while we cannot provide any results regarding this algorithm. The hyperclick miner has a low parameter robustness, but finds the relevant rule in all cases. GAR plus is not able to find the relevant rule at all. And also for use case 2, smaller data, variant 2.2, has no significant impact on the results. Let's come to a short conclusion of this work. We have shown that association remining is an appropriate technique to extract relevant process details from structured data, what we have shown here in case of image data. The hyperclick algorithm serves best for both scenarios, concerning parameter robustness and relevant rule detection. The approach with association remining is suitable for this purpose, also for small datasets. Future work should evaluate if further indicators or rule selection approaches are more suitable to select a relevant rule. Furthermore, they should focus on techniques to adapt the input data in complex scenarios, what is important when it comes to real-world processes. Thank you very much for your attention. Please get in touch with me if you have any questions.